Let's start with the computer vision session, okay? So it's a pleasure to have here Laura Leal-Taixé. She's professor at Technical University of Munich in the computer vision group. She's main research interests are video analysis and more specifically video object segmentation and object tracking. And she did the degree and the master in telecommunication engineering in the Universitat Politècnica de Catalunya. So let's start with her talk. Thank you.
Hello? Oh, okay. So today I will present a little bit of the work that we're doing at TUM. And my group is called Dynamic Vision in Learning. So it's obvious that we're interested in, of course, machine learning, but also dynamic vision. And by dynamic vision, I mean actually video analysis. So today I will present a little bit how can you actually take advantage of the temporal information that videos are providing you. So in classic scene understanding in computer vision, we actually want to understand every pixel of an image. So we look at the world through a camera, and by now we're actually pretty good at obtaining, for example, segmentation masks, so knowing the semantic meaning of each of the pixels that we're observing through the camera. At the same time, we're not only able to detect, for example, the class person, car, and road, but actually to separate the different instances. So for example, the different persons that we can observe in a scene. But the world is actually not 2D. We have a component that we often forget, and that is the time component. So we not only want to understand every pixel of an image, but we actually want to understand every pixel of a video. And for this, what we have to do is we have to get temporally coherent results. And so there are mainly two ways of dealing with this temporal information, with the time component. One way is to say, well, I just don't care, so I analyze every frame of a video independently, and I will present actually two works on video object segmentation and multiple object tracking that go more into that direction. So we don't care about the temporal component, but we still get temporally coherent results. And the second one is let's actually work with it. So let's work with the temporal component, with the temporal coherence. And I will also present a little bit of the work we did on a temporal discriminator for generative adversarial networks. So let me start with the first work that we did back in 2007. And that is about video object segmentation without temporal information. So in this case, we're working on the task of supervised video object segmentation. And this means that we have an input image and a given first ground truth mask. So we know actually which object do we want to segment throughout the video. And the goal here is actually to find this object in the subsequent frames of the video. And of course, if we look at the frame here, at the first frame here on the left, it will be rather easy to transfer the mask from the ground truth first frame that we have to this frame. The pose of the biker is rather similar. The background did also not change too much. But things start to get difficult when we go, for example, to this frame in the middle where the biker has completely disappeared, is completely occluded, or the last frame in which the pose and the background start to change significantly. So if we use classic techniques, for example, based on optical flow, we will encounter some difficulties already in this frame of the middle. So actually what we proposed to do was a rather simple method, fully end-to-end learn, which is called one-shot video object segmentation. And one-shot means that we're actually looking only at the first mask, so the ground truth mask of the first frame, and then we can follow the object throughout the video and throughout these other frames. Now, the key idea here is how we actually train this network. So if we look at any pre-trained network, for example, network trained on ImageNet, we know that this network is able to extract basic image features, edges, corners. So we see, for example, in this image here that we get some high activations on the edges of the image. Now, what we actually do is we take a video object segmentation benchmark, in this case the Davis benchmark, and we start training our network on top of ImageNet. And so now what the network is actually learning is it's learning to separate foreground from background. So for example, in this case, it will separate the crowd from the background, which are these buildings. So of course, this network is able to separate foreground from background, but it actually doesn't know what object in the foreground are we actually interested in segmenting. So this is why we perform a third step of training, which is only, we refer it as fine-tuning because we don't train for too long. And so we take this network, which we call the parent network, and we feed only one mask, so this first mask for which we have the ground truth, and we feed it to the network, and we fine-tune a little bit on this first mask. So essentially what the network is actually doing is it's overfitting to the appearance of this object in the first mask. And so by this, what the network actually learns is which objects do we want to actually segment. And so now we can take this fine-tuned network, apply it on every frame of the video, and we will obtain actually quite good results. So we can see that we can follow different types of objects. Of course, there's a fine-tuning step for each particular object that we want to segment. And we see that we obtain rather temporally coherent results, even though we didn't impose any constraints on the time domain. Now, another nice thing of the method is that it's actually pretty fast. So before this method, we had a bunch of state-of-the-art methods here depicted with all these different colors that use all kinds of optical flow and complex architectures, and were actually rather slow. So if we look now at, we have here in the x-axis the time per frame that the methods are actually taking to compute a segmentation mask, and the region similarity, which essentially means how good our mask is. So we can see that with our parent network, actually in just 102 milliseconds, we can get a pretty decent accuracy, so comparable to a lot of state-of-the-art methods at the time. And if we now allow the network to actually fine-tune on the first mask, we see that we easily outperform state-of-the-art methods by almost 12 percentage points. And this particular method here, which was state-of-the-art at the time, is based on object optical flow. So it should be temporally very coherent, but we can easily outperforming by doing this three-step training that I've presented. Now, other cool things about dealing with frames separately is that, of course, you don't have any problems with drifting or occlusions. So, for example, in this sequence where we have as a first mask, we have our biker here. This biker goes through a series of occlusions in this video, and you can see that these three occlusion here was actually a problem for previous methods. But since we're dealing with frames independently, it doesn't matter what happens in this occlusion. When the biker comes out of the occlusion, we will still be able to segment it. And the same happens with other types of occlusions where we might get some errors. The nice thing about this is that the errors are, of course, not propagated to future frames. So we can actually recover from bad masks that we get in the past. And so with this, we can actually get pretty accurate segmentations, even for these hard scenes, highly dynamic scenes where we have all these water splashes. We have these thin structures of the kite surfer. And also classically difficult scenes where there's a lot of post-change of the objects. There's a lot of occlusions also given by the smoke. But we can still recover pretty good the segmentation mask for these objects. Now, of course, one bad thing is that if we're actually dealing with a really highly dynamic scene like this one of the breakdancer, we can see that this one mask obtained from the second or third frame of the video, so pretty close to the ground truth first frame that the network has seen. But as we move along in the video, the breakdancer actually moves, and this second person here is revealed, and this person was actually occluded in the first mask of the video, which means that the network has never seen that this person should belong to the background. And so what can happen actually is that the network considers that this person is more similar to the foreground and so segments it also as a foreground object. So for this, I'm not going to go into detail, but we had a follow-up paper in a subsequent PAMI in which we actually use object proposals to counteract this effect and to get only one object out of the segmentation mask. Okay, so now I will move to another work that we did with a similar philosophy for multiple object tracking. And in this work here, we are still on the side of things where we actually don't care about temporal information. So we're actually going to perform tracking without actually performing tracking. So in the multiple object tracking setup, we have a set of videos, and the goal is actually to detect and track all the objects in the scene. And in this case, the representation of an object doesn't matter too much, but we're going to use bounding boxes. And so you can see that we actually have to deal with sequences of varying crowdness, varying viewpoints, illumination, and so this data is actually quite hard already to deal with directly. And most methods actually use the tracking by detection paradigm. So they step a little bit away from all the problems of viewpoint and illumination by first using a detector on each separate frame of the video to obtain a set of proposed locations. So the detector already gives you pretty good results nowadays, so we can trust that these results are actually depicting most of the pedestrians in the scene. And then what you do classically is you put a graphical model on top of these detections, and you try to input some or infer some of the temporal coherence through this graphical model. So essentially, the graphical model gives you the best explanation of trajectories for the set of detections that you're given by the detector. And well, this is still a deep learning symposium, right? So I'm not going to talk too much about the graphical model. So what about the learning? I mean, how much learning can we input in this particular pipeline? So we can actually learn the interactions, the cost that the graphical model needs to actually obtain this set of trajectories. And for this, we can essentially take some of the bounding box locations at frame t and the bounding box locations at frame t+1, and then use a Siamese neural network to actually tell you which bounding boxes belong to the same person. So this is actually rather straightforward and gives you pretty good cost that you can then feed into the graphical model. The problem here is that the graphical model is still the one that gives you the trajectories. So the actual optimization happens still at the level of the graphical model. And there is no feedback between the graphical model and the Siamese neural network. So the question that we wanted to answer for a recent submission was actually, can we make the full pipeline, the full tracking, can we solve it in a full end-to-end learned fashion? So can we learn both detection and tracking in one single step? And so for this, we actually had a look back into detectors. So there's a family of detectors, most notably fast and faster RCNN, that contain some key ingredients. So in this case, from an image, you run it through a series of convolutional layers, and then you have two heads, one that is actually giving you the probability that you are actually observing in a certain bounding box the class, for example, class pedestrian, class car. So this is what this head actually gives you. But there's a more interesting head for us, and that is the bounding box regressor. So what the bounding box regressor actually does is it takes your proposed bounding box and it refines its location. So it essentially tells you, it essentially snaps the bounding box to the actual location of the person. And actually, this is a pretty interesting thing, because what the bounding box regressor actually is doing is it's moving the bounding box to follow a certain, for example, person. So you know you have a person on the scene, you place a bounding box roughly on top of it, not really well placed, and this bounding box regressor will actually really snap it to where the person is. And so we thought, well, this bounding box regressor is actually performing tracking. So if we think about this, we can take the detections from the last frame. So the detections, of course, will be a bit misplaced because the person has moved from one frame to the other. But if we take actually the detections from the last frame as proposals and we pass it through this pipeline, now the bounding box regressor, what essentially will do is snap these bounding boxes to where the person actually is. So in the end, what the bounding box regression is doing is it's performing tracking. So if we now take this bounding box, we know that it has snapped to this new position, we assign it the same label, so we consider it's the same person, and we have now formed a trajectory of 2 detections. And so we actually found out that the bounding box regressor was able to tell us or to answer the question of where did the detection with ID1 go into the next frame. And this is essentially performing tracking. Now, of course, there are pros and cons with this method. The biggest pro is that all these regressors are extremely well trained with tons and tons of data. And there's far more annotated detections than annotated trajectories. So we can actually leverage that to get really well-positioned bounding boxes. But the biggest con is that this regressor only shifts the bounding box by a small quantity. So if we have, for example, large camera motions or large displacements due to low frame rate, we actually have to compensate a bit for that. Now, we can easily do that with the motion model, either a camera motion model or a pedestrian motion model. So this is something that is also classically used in the tracking community. And then the other con that we need to take care of is that in the end, there is no notion of identity. So if you have 2 persons that are crossing each other, the bounding box could snap into one person or into the other person. So the bounding box regressor has no notion of identity. So in order to close small gaps and to actually differentiate between these persons when they are really close together, we just simply use a re-ID method. So in re-ID, essentially you want to train a network that actually compares to bounding boxes and tells you whether these boxes belong to the same person or not. So the same thing that I've presented before can now be used here to disambiguate whether 2 boxes belong to the same person or not. Now, with these 2 cons and these 2 solutions, we actually have a pretty strong tracker. And by pretty strong, I mean that it clearly surpasses all other trackers by actually a fair amount. So if we look at the first column, here we have on 3 benchmarks the multiple object tracking accuracy, which essentially measures all sorts of views on the tracking problem, so from identity switches to misdetections to false detections. And we see that in some of the benchmarks, we actually have something like 4 or 5% of percentage points more in this MOTA value, which is actually quite a lot, considering that more or less per year, with all the papers that are published, CEPR, ECCV, etc., we get between 2 and 3 percentage points every year. So a jump of 5 percentage points is already quite a lot. And perhaps more interestingly, we can look at the second column. So the second column is the IDF1 measure. It's a rather new measure, but it actually tells you how well your methods are at keeping the identity of the persons. So I said that our bounding box regressor was not really strong at keeping identity, so there's no notion of identity, but still we get that we have a pretty good IDF1 measure. It's not state-of-the-art, really close to state-of-the-art with all these methods. And so, for example, here I've only plotted 4 methods, but there are more than 100 methods for each of the benchmarks presented here. So competition is actually quite fierce. And so the question is, well, it's strange because we did almost nothing. So we used already pre-trained architecture. We fine-tuned it a little bit for a specific case of person detection and tracking. And we already beat state-of-the-art easily. So the question is actually, what are these other methods doing? So what are they focusing on? What methods are they using? And why are they not good at the task of tracking? And so in the paper, we have a more thorough analysis, but I want to point out 3 key findings that we found during our analysis. One is that actually all the methods based on graphical models, which are supposed to be much better at recovering trajectories from occlusions, because you have connections from the beginning of the video to the end of the video. These are actually not so capable at recovering these occlusions. So the question is, if I have to use a complex graph model to recover occlusions and then I cannot do it compared to any regression-based model, then what is the point of using these graphical models on top of our detections? So actually, these are quite expensive to compute and solve. So the question is, why should we actually do this if we don't get better solutions than with our regression method? And another important thing is that all the re-ID measures or all the methods that actually use some form of re-ID are much, much better in what we call hard scenes. And I will actually define what we call hard scenes in the next slide. But the most important thing is that all methods are just kind of fighting to improve this 1–2% in easy scenes. And so what we actually propose is for all these easy scenes that are found in most tracking benchmarks, just use the detector. So this is capable of handling scenes where there are small occlusions, small interactions. And with a basic re-ID and motion model, we can actually get state-of-the-art results. And once this is done, the actual tracking can focus on the harder cases. And by harder cases, I mean, for example, long occlusions. So currently, trackers completely ignore that, because typically, if you allow your tracker to recover trajectories through the long occlusions, then you start creating a lot of false trajectories. So you start hallucinating people where there's no person. And of course, extremely crowded scenes. So this is something that we will present in a recently accepted CPR workshop, a new data set with really, really extremely crowded scenes. So this is it's gonna be fun to see what people do with that. And finally, just one nice thing about our method is that if you have any data set that contains detections, but you don't have a tracking data set, so you just have a bunch of images with a new object that you actually want to detect, you can still train the method and at the same time obtain trajectories instead of only detections. So this is a nice thing about the method, that you can easily transfer from detections to trajectories. Okay, so I've presented a couple of things on, we don't care about the temporal information, but now I actually do want to care about it. And I want to use the temporal information to obtain, let's say, nicer results when I analyze videos. And for this, we actually introduce the Temporal Discriminator, which we will plug into a GAN architecture and see how this can benefit our problem. So in this case, we're dealing with video super resolution. And that is the task where we're actually given a low resolution video, here depicted on the left. And we actually want to obtain a high resolution video. And so it is quite well known that this is a hard task, because we need to create a method that actually hallucinates details where, as you can see, there are not so many. And so for this, we actually we presented this recent work now under submission. And it's named TechoGAN. And of course, we use a generative adversarial network. And in this case, since we're dealing with videos, we have to generate one frame after the other. We use recurrent architecture. And so by recurrent, I mean that we're going to recurrently generate one video frame after the other. And we're going to take the previous high-res generated image as input for our generator. So we do want to generate coherent results by using this recurrent architecture. And now, of course, the GAN part comes when we when we add a discriminator to our architecture. In this case, I'm going to call it a spatial discriminator to differentiate it with a temporal discriminator. And what this discriminator is actually telling us is how real is the generated image. So in this case, you're actually judging the high resolution image by how real it is or how fake it is. And what this does, I mean, we all know GANs are actually pretty good at creating realistic spatial details. So with this architecture, we can actually get quite good details from the low resolution video. And so we can see, for example, this previous method on the left that contains all these weird details that it has hallucinated, while our method with the spatial discriminator on the right is actually much better at recovering these details. The problem here is that since we're actually processing, we still have this recurrent architecture, but essentially we're processing each frame independently. And so what the GAN is actually doing is it's creating the shard details in an inconsistent way. So it creates shard details in one image and then other type of sharp details in the other image. And this essentially causes a slight flickering that we see here in the video. And so our question was actually, how can we make the sharp detail generation more stable in time? And for this, we propose actually to use a temporal discriminator. So what a temporal discriminator does is it takes the same high resolution, low resolution, ground truth generated, all of these frames, but now instead of taking one frame, it takes 3 frames. So what this discriminator is now going to be able to do is it's going to be able to judge whether motion is real or not. So before we wanted to judge whether the image, the details of the image, the edges of the image, the structures that were hallucinated are real or not. This was the spatial discriminator. But with the temporal discriminator, we can actually ask the question whether this motion is real or not. And since we know how a real ground truth high resolution motion is supposed to look like, we can actually judge whether our generated high-res frames are also looking realistic in the temporal domain. And so if we actually do this, we can get much more coherent results, as seen here on the left, compared to only the spatial discriminator on the right. So this is a bit hard to see, but if you look at this part here, you see that there's actually quite a lot of flickering, while structures are much more stable here when we introduce the temporal discriminator. So of course, we needed a way to actually evaluate the quality, the temporal quality of our results. And for this, in the paper, we created several measures. So in this case, we're plotting a classic spatial detail measure, which is the LPIPS. And compared to a temporal coherence method, which we presented ourselves, which we call TLP. I mean, for more details, you can actually go to the paper where it's quite well explained. And the idea here is that the better results are in spatial detail if you look to the left. So this would be where the best result would be. And for the temporal coherence, it would be looking down. So overall, a method that has good spatial detail and good temporal coherence would lie here. And you can see that compared to other state-of-the-art methods, we are actually much, much better at keeping spatial detail while also providing temporal coherence. And here, the size of these circles actually represent the number of parameters that the models have. So you can see that also our model is actually pretty small. And this is because, so we tried to use a separate spatial and temporal discriminator, but we actually found out that we can fuse these two and use a single discriminator to actually perform both tasks while still keeping the model rather small. And so compared to other state-of-the-art results, we actually get pretty good details. So you can see here that the detail that is generated is actually quite impressive. And if we compare to other methods, we see that either we get sharper detail and more stable results, or for compared to the DUF method, for example, that has quite good temporal stability, we have much, much more spatial details. There are a couple more tricks, actually, that I welcome you to read in the paper, because I don't have time to explain them. But essentially, dealing with temporal information creates all sorts of funny artifacts. So we also introduce a ping-pong loss to get rid of these artifacts, and a couple other tricks that, that we actually put in there to get these cool results. Okay, so with this, I would like to thank you for your attention, and if you have any questions, I will be happy to answer them.